Hello everyone, welcome to our lecture video. In this lecture video, we are going to talk about calculation of deflection of beam by using Macaulay method. There are different methods to calculate deflection of beam, such as double integration method, conjugate beam method, and moment area method. We'll be talking about all those methods in our other lecture video. In this lecture video, we are going to talk about deflection of beam using Macaulay method. So our main aim is going to be calculating our deflection of beam. So we're going to explain this using our example. So let's say if we have a beam over here, and this is a simply supported beam. So we have a hinge load, and we have a hinge support and roller support. We have a hinge support at A, and we have a roller support at B, and we have our load, different loads acting. Let's say 1 kilonewton acting over here, which is at a distance of 1 meter. And next we have another load which is again of 2 kilonewton, which is acting at a distance of 1 meter. And we have another load which is 3 kilonewton, which is acting at a distance of 1 kilometer, and the remaining span is again 1 meter. So we have our total span of 4 meter, and we have a hinge support and roller support at A and B respectively. So we are going to calculate the deflection of this beam by using our Macaulay method. So you probably know what deflection means, but let me simply tell what deflection means. So we have a beam AB. Whenever some load is applied, the beam bends downward. The beam is going to bend in downward direction. This downward movement of beam due to load applied over it is called as a deflection. We are going to denote it as y. We are going to denote this as y. This is known as our deflection. And if I draw a line over here, and if I measure the slope, this is going to be my slope. If I measure the angle, what I have done simply over here is, so this is going to be my deflection. I have simply drawn one line, tangential line to this curve, and if I measure the deflection with my original beam, or with my original line, let's say theta A for point A, and for point B this is going to be my theta B. This is going to be known as my slope. So from our Macaulay method, we can calculate our both deflection, where we can calculate our deflection. This is my deflection y, which is my y. And we can calculate our slope as well. Slope is going to be my theta. So we are going to calculate both the deflection y and slope theta of this beam by using Macaulay method. So by the end of this video, we are going to be clear about what is Macaulay method and how it is applied with the help of this example. So for our Macaulay method, we need to understand few things, such as for our Macaulay method, we are going to take our flexural rigidity, which is known as EI. This is my EI. This is going to be constant. This is going to be constant if my flexural rigidity EI is not constant for overall beam. So from my point A to point B, what I'm going to assume is that my EI, which is known as my flexural rigidity, this is going to be constant. So for any cases where my flexural rigidity is not constant, Macaulay method cannot be applied. We can use another method, which is conjugate beam method, about which we'll be uploading a video shortly. So now for Macaulay method. So firstly, for our Macaulay method, so we're going to explain what we need to do is we need to calculate our support reactions. So for this, it's going to be my A, it's going to be my B. So I'm going to have one support RA over here. I'm going to have another support RB over here, and this is acting at a, now I have 1 kilonewton, 2 kilonewton, and 3 kilonewton over here. So we are going to simply calculate the support reactions RA and RB. So in order to calculate RA and RB, what we're going to do is we're going to take our upward forces as negative. We're going to take our upward forces as positive, plus Fy equals to 0. So it's going to be RA plus RB equals to, so we have downward force of 1, 2, and 3. 1 plus 2 plus 3. This is going to be RA plus RB equals to 3, 4, 5, 6 kilonewton. What we're going to do next is we're going to calculate moment. We're going to calculate right now we're going to calculate moment about A, and we're going to take clockwise moment as positive. So taking moment about A, so let me move on from here. I have 1 kilonewton acting at a distance of 1. So 1 into 1. So as you can see over here, if I put my point over here, and this 1 kilonewton is acting downward. This is acting in downward, and it's going to produce clockwise moment with respect to point A. Similarly, 2 kilonewton is also going to produce clockwise moment. 3 kilonewton is also going to produce clockwise moment, while 3 kilonewton, while my RB is going to produce anti-clockwise moment, because it's acting upward and it is pushing the beam in upward direction, producing anti-clockwise moment. So we have 1 into 1 plus 2 into 2 plus 3 into 3 minus RB into 3 into 3 minus RB into 4 equals to 0. So if I calculate, I'm going to get my value of RB from this as I'm going to get my value of RB. So let me put this name as C, D and E. So RB is going to be equal to 3.5 kilonewton. So my RA is going to be 2.5 kilonewton. So in this way, simply you can calculate your support reactions. Hope you are clear up to here. So let me rub all this part. So from here, firstly my important part is going to be my reactions. RA equals to 2.5 kilonewton, whereas RB equals to 3.5 kilonewton. So this, so my first and foremost step for my Macaulay's method to determine my deflection of the beam is going to be support reaction, and we have calculated our support reaction to be equal to be 2.5 kilonewton and 3.5 kilonewton. So after this, we are going to move on to our next step. So for our next step, as I explained before, I have my constant EI. So now for our next so firstly, after computing our reactions 2.5 and 3.5, what we're going to do next is we are going to apply this formula, which is EI d square y by dx square equals to mx, whereas which mx means our moment. So in order to calculate our moment x, we need to take a section xx, and while taking our section xx, we need to take the section in such a way that we incorporate maximum amount of force, maximum amount of forces, or maximum amount of reaction forces. So as you can see here, if I took my section xx at over here between A and C, all these forces 1 kilonewton, 2 kilonewton and 3 kilonewton are not going to be included. And if I took my section over here, let's say between C and D, then 1 kilonewton is going to be included, but 2 kilonewton and 3 kilonewton are again going to be excluded. So I'm going to so right now I'm taking my section between E and B. In this way, I have included all my forces 1 kilonewton, 2 kilonewton and 3 kilonewton. So first and foremost, we're going to calculate first and foremost, we're going to take a section xx, and we're going to calculate the moment about it. So next, what is going to be, next I'm going to write EI d square y by dx square equals to mx. So instead of mx, what we're going to write is, we have our support reaction. Let me write over here. For about A, we have 2.5 kilonewton, whereas about B, we have 3.5 kilonewton. So right now, again, we're going to take our clockwise moment as positive. So as you can see here, with respect to xx position, so right now I have kept a marker at xx section. So 2.5 kilonewton. So let me put it this way. My section xx is at a distance x from point A. So with respect to this, 2.5 kilonewton is going to produce clockwise moment. It's going to produce clockwise moment. So we're going to take it as positive. So firstly, we're going to have 2.5 x. So now we are moving for our next force, which is 1 kilonewton. So 1 kilonewton is going to produce, with respect to section x, it is going to produce downward force. Downward force means it is negative. But right now 1 kilonewton is acting at a distance of x minus 1. So as you can see here, up to here from A it is x, so but from C it is going to be x minus 1. We're going to subtract this one distance from the left, so it's going to be x minus 1 minus, because it is producing anti-clockwise moment, minus 1 into x minus 1. Similarly for 2, it's going to be minus 2 into x minus 2. And for similarly, let me put on the minus sign for 3 into x minus x minus 1, x minus 2, and 3 times x minus 3, not 2x minus 3, because this is acting, because on the left we have 3 meters, so remaining distance is x minus 3. So we have calculated our moment, and next what we're going to do is we're going to put this dotted signs to separate our forces, to separate our moments, to show our different moments. We're going to put this dotted signs. Next what we're going to do is let me take this as equation 1. Hope you are clear till over here. If you have any queries up to here, if you have understood anything, you can comment down below. I can answer you over there. So first, what we're going to simply do is we're going to integrate our equation first. We're going to integrate our equation first. So what we're going to do is we're going to integrate it. Ei d square y by dx square means dy by dx. So dy by dx means this means our so this is our slope theta. Our slope theta is denoted as dy by dx equals to 2.5. So integrating x, we're going to get x square by 2, so let me put on this dotted signs, minus 1 into x minus 1. So normally what happens in our integration is x dx equals to x square by 2, while x minus 1 dx, this is going to be equal to x square by 2 minus x. But in our Macaulay method, we are going to treat our x minus 1 as a whole x. We're going to treat our x minus 1 as x. So x minus 1 dx is going to be equal to x minus 1 whole square by 2. So in our Macaulay method, we're going to treat our x minus 1, x minus 2 and x minus 3 all as x only. So x minus 1, so x minus 2 dx for our next term is going to be simply equal to x minus 2 whole square by 2. We're going to simply treat our x minus 2 as x. So now let me continue my integration. My equation 1, minus 1 into x minus 1. So actually I haven't added over here, so there is a mistake till over here. So what happens over is 2.5 into x square by 2. So after integration I'm going to get one constant c1. So let me put on my dash sign, minus 1 into x minus 1 is x minus 1 whole square by 2. Again put dotted sign, minus 2 into x minus 2 becomes x minus 2 whole square by 2. We're going to treat all of them as x only, minus 3 x minus 3 whole square by 2. So it's going to be my so my second equation. So this is going to be my plus c1. Next final equation, I'm going to integrate equation 2 one more time, then I'm going to get ei dy by dx becomes y. This is equal to 2.5 x cube divided by 2 3 are 6. So integration of x square dx is simply going to be x cube by 3. I already have 1 by 2 in denominator, so it's going to be x cube by 6. So now x cube by 6 plus c1, integration of c1 becomes c1x. So I'm integrating second time, so I'm going to get another constant c2. Let me put on my dotted sign, minus. So by keeping dotted sign, we are just separating our sections. Minus 1 into x minus 1. We're going to treat x minus 1 as x. So we're going to get x minus 1 is going to be x minus 1 whole cube by 6, minus 2 into x minus 2 whole cube by 6. Again put on dotted sign, minus 3 times x minus 3 whole cube by 6. So this is so let me so now we have our this is my slope equation. From this I can calculate my slope, and this is my deflection equation. This is my slope equation. From this I can calculate my slope for all the beam, and from this I can calculate my deflection. But right now we have two variables, c1 and c2, and we need to find the value of these variables. So right now this is my deflection equation, 2.5 x cube plus c1 x plus c2. So as I told before, I need to find my value of c1 and c2. So firstly, what we're going to do, in order to find our value of c1 and c2, we're going to apply boundary conditions. So what are the boundary conditions? Boundary condition means we're going to apply the condition of point A and point B. So if I draw the deflection curve, what is going to happen is my beam is going to be deflected in this way. It is going to deflect in such a way at support reactions A and B. I'm going to have at A and B I am going to have I'm going to have zero or minimum deflection, while at the middle I'm going to have maximum deflection. It's going to be my y max. So while the deflection at this point at ya is going to be 0, and at yb is also going to be 0. So we're going to utilize this condition. It's going to be my boundary condition in order to find the value of c1 and c2. So applying boundary conditions at x equals to 0, which means at point A my deflection ya equals to 0. So what I'm going to simply do is I'm going to value x, I'm going to substitute the value of x and y in equation 3. So ei into y is 0, so my left hand is going to be 0. So 2.5 into 0 cube by 6 plus c1 into 0 plus c2. So right, another rule regarding Macaulay's method is that in Macaulay's method what we're going to do is, if we get our any term, if this bracket term is going to be less than 0, this is going to be less than 0, we're going to ignore that term. So this is our general rule, this is our second rule regarding Macaulay's method. So our first rule was treating x minus 1 and x minus 2 as x, while our second rule is that if I get my if my term inside of this bracket is going to be less than 0 or negative, we're going to ignore that term. For instance, so if I put my value of x over here in x minus 1 cube divided by 6, is going to be 0 minus 1, which means minus 1 cube by 6. So we're going to ignore this term. Similarly, for this term x minus 2 cube by 6, if I put my value of 0 over here, 0 minus 2 minus 2, so we're going to ignore this term. Similarly for all this term. So from here what we're going to get our value of c2 as 0. So we have got our value of c2. Now we're going to need our value of c1. So now to get our value of c1, what we're going to do is we're going to apply our second boundary condition, which is at x equals to 4 meter, which means at our point B, again our deflection yb equals to 0, as I explained before. At our support reactions point at A and B, always the deflection is going to be 0. So next what we're going to do is yb equals to 0, so our left hand equation is going to be 0. So 2.5 into we're going to put the value of x as 4 cube by 6 plus c1 into 4, while my c2 is going to be 0 again. So now if I put 4 over here, 4 minus 1 is 3, so this time it is not less than 0, so we're going to include that term. Minus 4 minus 1 is 3 cube divided by 6, minus 2 into 4 minus 2 cube by 6, minus 3 into 4 minus 3 is 1 cube by 6. So I'm not going to teach you basic maths. You can simply calculate this and we're going to get your value of c1. So we're going to get your value of c1, which is going to be equal to, so your value of c1 is going to be equal to minus 4.75, and your value of c2 is going to be equal to 0. So what we're going to do next is we're going to simply use this value and simply substitute the value of c1 and c2 in equation number 3. In equation number 3, which is going to be my deflection equation. So let me rub this. So we're going to substitute our value of c1 and c2 in our previous equations. So let me show you my previous equation. So this is my deflection equation, while my slope equation equals to this is 2.5 x cube divided by 6, while my previously I had found out my deflection equation as 2.5 x square by 2 plus c1 plus c1 minus 1 x minus 1 whole square by 2 minus 2 x minus 2 whole square by 2 dot minus 3 x minus 3 whole square divided by 2. So this was my previously equation 2. So this is my slope equation, well this is my deflection equation, and I calculate my value of c2 as 0, while my value of c1, we calculate our value of c1 to be equal to minus 4.75. So what we're going to do next is we're going to simply substitute the value of c1 and c2 in this equation. So my c2 is going to be 0, so we're going to simply rub c2 and my c1. So let me just put this as c1 is going to be equal to so let me just remove this plus sign as well. So this is going to be minus 4.75, and over minus 4.75 x minus 4.75 x. And for this equation I'm going to rub my c1 and I'm going to get a value of c1 as 4.75. So this is going to be my slope equation, and this is going to be my deflection equation. So now, having these equations, we can easily calculate our value of deflection and slope for any point on this beam. So let's say if I have to so let me firstly calculate my deflection. So using this I can so let me rub this. So now using this, let's see if I have to calculate deflection at point A. So as I already explained before, deflection at point A is going to be 0. So I don't need to calculate that. But let me show when x equals to 0, deflection at A, y A equals to, so what I'm going to simply do is I'm going to substitute C in this equation, equation number 3, because this is my deflection equation. So I'm going to get x is 0, so let me put if I put so let me show when x equals to 0, which means this equation is going to be 0, this equation is also going to be 0, and again if I put a 0 over 0 minus 1 is minus 1, so we're going to ignore this. 0 minus 2 minus 2, again ignore this. 0 minus 3 minus 3, so we're going to ignore that. So our first term is 0, and so we're going to simply get our ya as 0. So now when x equals to 1 meter, we're going to get deflection at point C, yc. So we're going to get our deflection at point C, yc equals to 2.5 into 1. So I'm going to simply put 2.5 into 1 divided by 6 minus 4.75 into 1 minus 1 minus 1 is 0, so 1 minus 1 is 0, 0 by 6 is 0, so 1 minus 2 is minus 1, 1 minus 3 is minus 3, so we're going to ignore both of these terms. So whenever we get our term less than the 0 or we get our term negative, we're going to ignore those. So if we solve this, so we have by EI, which is our flexible rigidity in our left hand side, so we're going to get yc simply as 2.5 into 1 by 6 minus 4.75 into 1, this is going to be equal to my deflection at point C is simply going to be equal to minus 4.33 divided by EI. So in this way you can calculate your deflection for other point as well. So what you need to simply do is, so let me just do it quickly. So when x equals to 2 meters, we're going to get deflection at point D, YD. So what you need to do is you need to simply put 2 over here, 2.5 into 2 cube divided by 6 minus, so we're going to put 2 over here, 4.75 into 2, 2 minus 1 is 1 cube by 6, so we're going to put that. 2 minus 2 is 0, so we don't have any of this, we're not going to include this term because it's 0, and 2 minus 3 cube by 6, which means we're again going to get negative term, so we're going to ignore this term. So we're going to simply get 2.5 into 2 cube by 6 minus 4.75 into 2 minus 2 minus 1 is 1 cube by 6, and we're going to get our deflection at point D as minus 6.33 divided by EI. Simply now for x equals to 3 meter, what we're going to simply do is we're going to substitute 3 over here. We're going to put 2.5 into 3 cube by 6 minus 4.75 into 3 minus 3 minus 1, which is 2, which is positive, so we're going to include this value, minus 2 cube by 6 minus 2 into 3 minus 2, 1, which is again positive, so we're going to include this value as well, minus 3 minus 3 is 0, so this value is going to be 0. So on doing this, we're going to get our value of ye. So when we have 3 meter, we're going to raise ye, we're going to get our value of ye as minus 4.667 divided by EI. So in this way we can calculate our deflection. So we're going to do the same for our slope as well. So in order to calculate our slope, so let me put on my slope. So for our slope, so when x equals to 0, I'm going to get my theta a, so y becomes theta. So let me drop all this. So when x equals to 0, theta a equals to something. When x equals to b, y c equals to something. So first to calculate our slope, so there is a mistake over, it's not plus, it's going to be minus, because we calculated our value of c1 as minus 4.75, so this is a slight mistake over here. So simply put the minus sign over here. So minus sign over is going to be minus 4.75. So in order to calculate our slope, we're going to substitute the value of x over here in our slope equation. So when x equals to 0, if I put my value of 0 over here, so this is going to be my first equation. So my first equation is going to be 0, so I have minus 4.75 divided by EI, because all the remaining terms are going to be less than 0. 0 minus 1 minus 1, 0 minus 2 minus 2, 0 minus 3 minus 3. So we're going to ignore all the remaining terms. So we're going to simply have minus 4.75 divided by minus 4.75 divided by EI. So when x equals to 1 meter, we reach our point C. So simply substitute 1 over here. It's going to be 2.5 into 1 square, 1 by 2 minus 4.75 minus 1 into x minus 1 whole square by 2. So 1 minus 1 is 0, so this term is going to be 0, while 1 minus 2 is minus 1, so this term is going to be neglected. 1 minus 3 minus 3, 1 minus 3 is minus 2, so this term is going to be neglected as well. So this is our second rule for our Macaulay's method, divided by EI. EI is on our left hand side, so we are going to get our theta c value as we're going to get theta sub as minus 3.5 divided by EI. Similarly, when x equals to 2 meter, I'm going to reach my point D, so I can calculate my slope in that case as theta d equals to, simply substitute 2 over here, 2.5 into 2 square by 2 minus 4.75 minus 1 into 2 minus 1. So we're going to include this equation this time, because 2 minus 1 is 1, 2 minus 2 is 0, so so 0 has no value. 2 minus 3 is 2 minus 3 is minus 1, so we're going to ignore this term. So we're going to get our theta d as minus 0.25 divided by EI. Similarly, for our theta e, we're going to substitute 3 over here, 2.5 into 3 square by 2 minus 4.75 minus 1 into 3 minus 1, which is 2, so is positive, so we're going to include this. 3 minus 1 square divided by 2 minus 2 into 3 minus 2 whole square by 2. 3 minus 2 is 1, so we're going to include this. 3 minus 3 is 0, so this term is has no value. So so on calculating, we're going to get our theta e as 3.5 divided by EI. And finally, when substituting x equals to 4 meter, we're going to 2.5 into 4 square by 2 minus 4.75 minus 4 minus 1 3 included, 4 minus 2 2 included, 4 minus 3 1 included. So we're going to get our value as finally 5.25 divided by EI. So in this way, using Macaulay's method, we can calculate our deflection as well as slope for our beam. So hope you liked our content, and if you have any queries, we can comment down below. I'll try to I'll try to clarify you over there. And if you like our content and if you want to support us, do subscribe the channel and share with your friends. Thank you.